Chapter 26, the capacitance. Here in this chapter, we want to study many configuration of capacitor. First of all, I want to take and I want to calculate the capacitance for parallel plates. I mean, we take two identical plates. Each one has an area A, for example. They have the same area with a separation D between them. These plates can be a rectangular, can have a rectangular shape. They can have a circular shape. The second configuration, before. In this case, if we have two identical plates, we get a uniform electric field between them. Okay. Now the second case, we take a cylindrical configurations where we have a empty shell, cylindrical shell conducting object. Inside we put a cylindrical rod. Uh, Out we have a positive charge, a negative charge, and inside we have a positive charge, and we have to study the capacitance of this capacitor. And the third case, I take a capacitance with a spherical configurations where we have a spherical shell negatively charged. Inside we put a positive spherical metallic object, and it will be a conductor, a capacitor. We have to study the capacitance of this object. Anyway, we talk about each configurations in details later. Now, let me start with a simple discussion. We have in general what I mean by capacitance. The capacitance, capital C, equals to Q divided by delta V. Here, I take a simple small conducting objects, okay, identical. It can be plates, it can be any conducting objects. Initially, we have a small left one, A, and the right one, B. Initially, we don't have Q. Q equals to O for both sides, okay? And also, as we don't have a field between them, in general, delta V equals to, let's say, VB minus VA equals to minus E dot delta X between A and B. If we have field between the objects, we can get a difference of potential. As we don't have Q, so we don't have a field between them. We don't have field, so we don't have a difference of potential. Delta V equals to O. We can say VA equals to VB equals to 0. Or at least VA equals to VB. Okay. How can we create a field between the plates? Simply, we have to put some quantity of positive charge here and a negative charge here. We can create an electric field between them. How can we do this? We can add simply a battery here. We have a positive side and negative side. Let's say we have side A and side B. Here we have side small a and side small b. Initially we don't have Q. We can connect the left side of the battery, the positive side, to the left conducting object, and the right one to the negative side. This side will be charged with plus Q, and this one minus Q. we continue to the final state. At the final state, we get VA equals to VA and VB equals to VB. And we have a positive charge here and a positive charge here. Okay, so we create an electric field between them. If we increase the value of Q, we increase the value of E. At this point, we can say delta V or VB minus VA equals to minus E dot dx. So we have an electric field and we have a difference of potential between A and B. Okay, and you know delta V between A and B equals to delta V between capital A and capital B at each extremity of the battery. Okay? Okay, now you know the positive side of the conducting objects is the high electric potential, and the right one of the negative side has low electric potential. You know. So VB minus VA must be negative because you, for example, you have the low potential minus the high potential. So the quantity here must be negative. But we are talking about delta V. Delta V must be positive delta V. In this case, we can say delta V equal to the absolute value of VB minus VA. So this value must be positive. So now what about the capacitance? The capacitance equals to Q divided by delta V. We can say simply the capacitance is how much charges added to the conducting objects to create an electric field E with a potential delta V. Okay, it's simply we can write this definition. The quantity of charge added divided by the difference of potential between the conducting objects. Here we can say with a potential okay. Anyway, delta V. Now, what about the geometry of this capacitor? You know, here I take a special case with two identical conducting objects. Okay, initially we don't have charge. We can add a battery on the system, plus and minus. So we can charge each side. We get finally plus Q and minus Q. You know, at the final state between A and B, VB minus VA equals to minus EDX between A and B. E is constant, so we get finally minus E dot D. Is constant because we have a parallel plates identical, so E between them is constant. So we have delta V and delta V. We can say here, for example, we have delta V equals to 1.5 volt. So delta V between A and B must be the same. Okay. In the case where delta V equals to the absolute value of VB minus VA equals to 1.5 volt. It's a positive value. Now, what I have to do? I have to change the distance between the plates. I want to decrease the distance between them. So we can push this side. Okay. Now they are closer. We can change the configuration. Okay. We decreased the distance. Okay. You know, VB or delta V equals to E times D. The absolute value of VB minus VA equals to minus ED. So the absolute of this one equals to ED. Okay. Delta V equals to ED. Now we decreased the distance between the plates. You know, delta V is constant. Why? Because we have a constant, the plates are connected to a constant value. We can say here simply, so we can say as the plates are connected to the battery, the potential difference is constant through the plates equals to delta V AB equals to 1.5 volt. Okay, we have delta V constant, so the total value here must be constant. If we decrease D, so E must be increased, okay, to get a constant value as result. How can we increase E? By increasing the charge, okay? So if the field increased because the increasing of charge. In this case, we can say finally C equals to Q divided by delta V. If we increase Q, delta V is constant, so C increases. Okay, it's a simple relation. We can say here by so we can say the potential difference is constant. Delta V is constant. Okay, by decreasing the distance D between the plates, the electric field increases by flowing more charges to the plates. Q increases, delta V is constant, so C must be increased. Okay, now let us take another case. What's happening if we replace the small conducting spheres with large conducting plates? Okay, we had before two small conducting objects, and we want to put in the place a large plates. Okay, in this case, the plates can hold a lot more charge. If we increase the area of these plates, Q will be increased. delta V is constant because it's connected to a constant value of delta V, so C must be increased. So, so we have two cases now. If we decrease the distance between the plates, C increases. Also, if we uh, change the small conducting spheres to the large conducting plates, also C increases.